Good afternoon, friends. First of all, introduce myself. My name is Ashok Patel. I am working as an assistant professor in Hasmukh Goswami College of Engineering. So, and my today's lecture topic is system of linear equation and matrices. So, today's lecture I am going to present the how system of linear equation solved by the matrices. So this is the content of my lecture: introduction to system of linear equation, solution of system of linear equation, Gauss elimination method and Gauss-Jordan elimination method. Before we introduce the system of linear equation, we have to know about the matrix. So what is matrix? Matrix is an ordered rectangular array of numbers or any abstract quantities. This is called the matrix. And there are many applications of matrices in mathematics, like graph theory, cryptography, etc. And one of the best application is how solve this linear system by using the matrix. So a matrix with m rows and n columns denoted by m by n, and it is defined by this fashion: A is equals to A11, A12 up to A1n, second row A21, A22 up to A2n, and continuously up to mth row AM1, AM2 up to AMN. So in this slide you can see the matrix with m rows and n column. Now introduce the system of linear equation. So what is the definition of system of linear equation? A finite set of linear equation with n variables x1, x2 up to xn is called a system of linear equation or linear system. And this equation with n unknowns, it can be written in this equation. Let a11 x1 plus a12 x2 plus up to a1n xn is equals to b1. Second equation, a21 x1 plus a22 x2 plus up to a2n xn is equals to b2. And continuously with mth equation, am1 x1 plus am2 x2 plus up to amn xn is equals to bn. And notice that the b1, b2 up to bm are constant. And this in this slide you can see the equation of linear equation with n unknowns. So its matrix form, it can be written in this form: x is equals to b. So what is a? A is the a11, a12, a1n, a21, a22, a2n up to am1, am2, amn. This is the matrix with m rows and n column. And x is equals to column matrix with entries x1, x2 up to xn, and b is the constant matrix with b1, b2 up to bm. And argumented matrix. What is the argumented matrix of the system? So argumented matrix of the system can be written in this mutually with the coefficient matrix and the constant matrix: a11, a12 up to a1n, b1, a21, a22 up to a2n, b2 up to so on. So this is the called argumented matrix of the system Ax is equals to b. And in the linear system of equation, there are two types of linear system of equation: non-homogeneous equation and homogeneous equation. So what is the non-homogeneous equation? Non-homogeneous equation is written in the form Ax is equals to b, and homogeneous equation is of the form Ax is equals to 0. Now we classify the solution in the case of non-homogeneous equation. There are three types of solution in non-homogeneous equations. First one is unique solution, second is infinitely many solution, and third one is no solution. See the current slide. The geometry behind the non-homogeneous equation. For that, let two equation of line a1x plus b1y is equals to c1, that is line L1, and take another equation of line a2x plus b2y is equals to c2 L2. Now see the first case. The two line L1 and L2 intersect at a unique point, and that is the case of exactly one solution or the unique solution. And see the next second picture. L1 and L2 two lines are parallel, so that means the two lines are not intersect at any point, so this is the case of no solution. See the picture, third picture, that is two lines L1 and L2 are coincide. That means this is the two line intersect at infinitely many points, and this is the case of infinitely many solution. Now solution of homogeneous equation. There are two types of solution in homogeneous equation. First one is trivial solution. In this case all the unknowns are 0. The second case is infinitely many solution, same as the non-homogeneous equation. And the geometry behind the homogeneous equation, let two line a1x plus b1y is equals to 0, and notice that the constant part in the homogeneous is 0. That is the line of L1, and consider second line a2x plus b2y is equals to 0, that is line L2. And see the first picture. The L1 and L2 line intersect at the origin, at the 0, 0 point. So in this case we can say that that is the case of trivial solution. All the unknowns x and y are 0. And look at the second picture. L1 and L2 line passing through the origin, but coincide two lines L1 and L2. So that is the case of infinitely many solution. Before going to discuss the solution, we have to know about the consistent and inconsistent of the system. If a system of equation has at least one solution, it is called the consistent system. If it has no solution, then it is called the inconsistent system. We have to familiar with the quantity, elementary row operation, back substitution, row equivalent form of a matrix, and reduce row equivalent form of the matrix. First of all, elementary row operation. There are three elementary operation in matrices. Interchange any two rows, that is the first row operation. Second operation is multiply any row and with any quantity, constant quantity, that is the second operation. And third operation, add one row to the another by multiply with some constant number. That are the three elementary row operation. In this slide, notation for row operation. If let Ri denote the ith row of a matrix, then first notation Ri Rj to mean interchange row I with row j, and the second operation C times Ri to mean that replace row I with C times row I, means multiply row Ri by the constant number C, and the third operation Rij with K to mean that add row I to the row j with K times of row I, means that multiply row Ri with constant K and add to the row j. The back substitution. For that we consider the one system x plus y plus 2z is equals to 9, and second equation y minus 7 by 2z is equals to minus 17 by 2, and the third equation z is equals to 3. In this system we easily determine the value z is equals to 3. Put this value in second equation, we get the value of y. Put this two value y and z in the equation 1, we get the value of x. This process is called the back substitution, and solution we get in this back substitution using back substitution is x is equals to 1, y is equals to 2, and z is equals to 3. Row equivalent form of a matrix. What is row equivalent form? If any matrix satisfy this three condition, then we say that the matrix is in row equivalent form. First condition, each row 0 of the matrix occur below a non-zero. Second condition, the first non-zero entries in each non-zero row is 1, and that 1 is called a leading one. And the third condition, in any two successive non-zero rows, the leading one in the lower row lies to the right of the leading one in the upper row. Let some examples of the row equivalent form. Let first example of the row equivalent form, the 0 rows below the non-zero rows, and the second condition, because of the second condition, in the non-zero rows first element must be the 1. Let consider second example. In the 0 rows occur the below non-zero rows, and upper top row is 1, and second leading one position, see there, that is also 1, that is the highlight by red color. And the third example of the row equivalent form. This is the reduced row equivalent form of a matrix. If the matrix is in row equivalent form, that means satisfy the three condition of row equivalent form and plus one condition. If a column containing leading one, then the other entries in that column are zeros. Means if in row equivalent form, the leading one, if any column contain leading one, then except that leading one entries, all the entries in that column must be 0. And that are some examples of reduced row equivalent form. See the second example, that is the position of first leading one, and in that column all the entries except this leading one is 0, and that is the position of second leading one, and all the other entries except this is 0, and see third position of leading one, and except this the values are 0, and that is the third example of reduced row equivalent form. So that how the row equivalent form and reduced row equivalent form can be see. Now take one example to any arbitrary matrix converted to row equivalent form. For that example, we take one example. Find a row equivalent form of the following matrices. For that solution, see the given matrix. The top non-zero rows and the first element is 0, but because of the row echelon form conditions, there is must 1. For that we take operation R1 R3, that means interchange R1 to R3 row, and resultant matrix is given 1 3 minus 1 2 2 3 4 5 0 minus 1 2 3 3 2 4 and 1. Now see this matrix. Because of the row echelon form condition, below the leading one entry, all the entries below the leading one must be 0, but here in the second row there is 2 and the fourth row there is 3. So reducing these entries to 0, we take operation R12 minus 2, that means add first row to the second with the multiply by minus 2, and take simultaneously second operation R14 minus 3, that means multiply first equation by first row by minus 3 and multiply add in the fourth row. So resultant matrix is given in given this matrix. So now note that in this matrix because of the row echelon form condition, the second after the first position of leading one, the second position of the leading one must be there, but the current value is minus 3. So converted that minus 3 to the 1, we interchange this row, second row, by the third row, doing this operation R2 to R3. After this row operation, the matrix is given 0 minus 1 2